Hi everyone, I am Madam Rosmaya. Welcome to my YouTube channel. In this video, we are going to discuss on molecular kinetic energy. Okay, so good morning everyone. Our topic for today is molecular kinetic energy. Okay, so we have learned, you have learned before in your secondary school, Form 4, Form 5, that temperature of a gas is proportional to the mean translational kinetic energy of all of the gas molecules. As the temperature increase, so the kinetic energy also increase. Okay, shown by the animation here. So the first diagram show the speed of the molecules with the higher kinetic energy. Means more thermal energy. So the second one, less thermal energy. So the speed is less. So from the kinetic energy, generally the equation is half mv squared. So you can see the difference between the two animation. So for Form 6 level, okay, we are going to prove this, to prove how the temperature, uh, how the kinetic energy is directly proportional to the temperature. Okay, these three formulas we have discussed before. Okay, I hope you all have memorized all these formula and how to derive them. Now we continue with the empty one here for the kinetic energy. To be put here, the kinetic energy formula. Okay, we start with, we are going to use this one, dense pressure, pressure, pressure of a gas equals to 1/3 N per V M mean square speed. Okay, so N is the number of molecules, V is the volume, M is the mass of one molecule, and this one is the mean square speed of a molecule. Okay, and then translational kinetic energy is equals to half mv squared. Okay, so we are going to relate with the kinetic energy from the equation here. Okay, so we use, we cross multiply V, becomes PV equals to Nm square root, mean square speed per 3. And then also from the equation, PV equals to nRT. Okay, so I didn't show here. So we use PV equals to nRT. So we combine these two, okay, equate them, we get nRT equals to Nm mean square speed per 3. Okay, now we cross multiply 3 nRT per n. Okay, on the right side become m mean square speed. Okay, how to relate with kinetic energy? We have half here. So therefore, we multiply by half both sides of the equation. So we get 3/2 nRT per n. And then here is 1/2 m mean square speed. So we multiply by half both sides. We get this. Okay, so this is kinetic energy. Half m mean square speed is a kinetic energy. Okay, so we can rewrite this equation into another form using n number of moles equals to number of molecules per Avogadro number. Okay, this one we've discussed before in the previous lesson. So we can substitute into the equation here, this n. So we can cancel out the n, big letter n here, capital letter n. Okay, so the equation, this equation becomes 3RT per 2Na. Okay, so equals to kinetic energy. Okay, so this is another form of kinetic energy. Okay, translational kinetic energy or mean translational kinetic energy. So we have two equations already. And we can also use Boltzmann constant K equals to R per Na, Avogadro number. Okay, so we use this, we substitute into the equation above, the R here. Okay, so we can cancel out the Na. Okay, Na, Avogadro number, so we get 3 kT per 2. So altogether we have 3 equations to be memorized for the mean translational kinetic energy. Okay, so all these 3. And don't forget also the kinetic energy means translational kinetic energy equals to half m mean square speed. Okay, so we can actually before that, so mean translational kinetic energy of a molecule is directly proportional to the thermodynamic temperature. So it is proven by the equation we have derived. Okay, so here T, all here we have T, and this is kinetic energy. So kinetic energy is directly proportional to the T temperature. Okay, so that's mean the heating, okay, when we do the heating process, it will cause the molecules to speed up. Okay, and therefore the temperature increases. Okay, so we have proven how the temperature relates with kinetic energy. Okay, so we can also write like this. Okay, this is all the formula to be memorized. So we can include in this slide the another part for formula for the kinetic energy. Okay, so we try example related to mean translational kinetic energy. So we try this example. What is the mean translational kinetic energy of molecules in an ideal gas at 57 degrees Celsius? Okay, temperature is given 57 degrees Celsius, only temperature given. So remember that always convert the temperature given if in degrees Celsius to Kelvin. Okay, so we convert 57 degrees Celsius plus 273, we get 330 Kelvin. Okay, so to find mean translational kinetic energy, okay, from the 3 equations just now, we choose one. Let's say we choose 3 kT per 2. Okay, so go back to the equation here. So you just choose one, the most suitable. Okay, sometimes can use more than one equation. So let's say we choose 3 kT per 2. Okay, so Boltzmann constant is 1.38 times 10 to the power of negative 23 joule per Kelvin. So this is Boltzmann constant. You substitute into the equation here with the temperature 330. So you get the answer 6.83 times 10 to the power of negative 21 joule. So this is the mean translational kinetic energy. Instead of using this equation, you can also use 3RT per 2Na. You will get same answer. Okay, so if you use 3RT per 2Na, so the R, the gas constant is 8.31. Okay, absolute temperature 330. 2 times Avogadro number 6.02 times 10 to the power of 23. So you will get same answer. Okay. So simple question. I hope you all can understand this example. So we go to the next example. Okay, estimate the mean translational kinetic energy of helium atoms at 300 Kelvin. Hence, deduce the RMS speed of helium atoms at 300 Kelvin. Okay, so now we are going to relate kinetic means translational kinetic energy with the RMS speed. Okay, so we have discussed before the RMS speed. So today we just do revision, combine these two formula, the last week lesson and with today's lesson. Okay. And then given that mass of helium atom is 6.6 times 10 to the power of negative 27 kilogram. Okay, so what would be the RMS speed of helium's atoms at 400 Kelvin? So we do the for 300 Kelvin first. Okay, so means translational kinetic energy first. So we can use kinetic energy equals to 3 kT per 2. Okay, because mass is given. So we can use 3 kT per 2. So we substitute the Boltzmann constant. Then 300 Kelvin, already the temperature given already is in Kelvin, then per 2. So you get the kinetic energy 6.21 times 10 to the power of negative 21 joule. Okay, done for the first part of the question. Okay, next the question is deduce the RMS speed. Okay, so for the RMS speed, so we use the second part half m mean square speed per 2. Okay, so this one. So the kinetic energy calculated already. Okay, so we substitute into here. Okay, kinetic energy is equals to half m mean square speed. So half m is given 6.6 times 10 to the power of 27, and then the mean square speed. So we calculate the mean square speed. Okay, so the mean square speed is cross multiply. Okay, we get this. So the answer for the mean square speed is 1,818 meters squared per second squared. Then we, to get the RMS speed, so we square root the mean square speed. This one is from the previous lesson. So RMS speed equals to square root of the mean square speed. So you square this value, so you get 1.37 times 10 to the power of 3 meter per second. So this is the answer for the RMS speed. Okay, can you remember or not the previous lesson? Okay, so this is the answer. Any problem? No, Okay, for the second part of the question, the third part, So what would be the RMS speed of helium atoms at 400 Kelvin? So you do the same method. Okay, the 300 you replace with 400. Okay, so you just replace with 400 and calculate the kinetic energy. But the questions doesn't want the kinetic energy for the helium atoms at 400 Kelvin. So you can straight away use this equation. 3 kT per 2 equals to half m mean square speed. So you directly substitute 3 Boltzmann constant 400 Kelvin here per 2, then half m mass of the helium mean square speed. So you get the mean square speed, this value, then for the RMS speed, square root of this value. So you get 1.58 times 10 to the power of 3 meter per second. So we skip the kinetic energy part because the question doesn't want the mean translational kinetic energy at 400 Kelvin. So it depends on the question actually what they want. Okay, so any problem before we continue to the third example? So if no problem, okay, silent means understood, right? So we go to the next question. Okay, so the next question is harder a little bit. So the essay question or subjective question, so will be like this lah. they will combine the question, what we've learned before in the previous lesson, combine all together. So question A, how many atoms of helium gas fill a balloon having a diameter of 30.0 centimeter at 20.0 degrees Celsius at 1.00 atmosphere? And then question B, what is the average kinetic energy of the helium atoms? So average kinetic energy is equals to mean kinetic energy, same thing. So sometimes the question will use average kinetic energy. Okay, question C, what is the root mean square or RMS speed of the helium atoms? Okay, so we do A first. How many atoms of helium gas fill a balloon having a diameter of 30.0 centimeter at 20.0 degrees Celsius and 1.00 atmosphere? So from PV equals to NKT, so we use this equation because given in the question is pressure, 1.00 atmosphere is pressure. And then from diameter here, 30.0 centimeter, diameter of the balloon, we can calculate the volume. Okay, we can use here volume. Okay, so N is what the questions want, how many atoms. So we are going to find N. Okay, K, Boltzmann constant, and temperature 20.0 degrees Celsius. So convert to absolute temperature in Kelvin. Okay, so that's why we use PV equals to NKT. Okay, so we arrange the equation to get N equals to PV per KT. Okay, so the volume, for the volume, we assume that the balloon is a spherical shape, okay, in a spherical shape. So we can use the equation 4 per 3 pi r cube. Okay, volume of a sphere 4 per 3 pi r cube. Okay, so for pressure, 1 atmosphere is equals to 1.013 times 10 to the power of 5 Pascal. So how to convert atmosphere to Pascal? So you must know. Okay, so 1 atmosphere is equals to 1.013 times 10 to the power of 5 Pascal. So we use SI unit. And then the 4 per 3 pi r. So the radius of the sphere, okay, the balloon is in the sphere shape. So diameter is 30 cm. So radius will be 15 cm. So convert to meter becomes 0.150 meter. And then the Boltzmann constant is 1.38 times 10 to the power of negative 23. And lastly, the temperature is 20 degrees Celsius plus 273. So we convert this to Kelvin. So we get the answer, okay, number of molecules equals to 3.54 times 10 to the power of 23 atoms. Okay, so this is the answer for question A. Okay, any problem with question A? Okay, no problem. So we go to question B. What is the average kinetic energy of the helium atoms or mean kinetic energy? So for question B, we use kinetic energy 3 kT per 2. Okay, so we substitute the values of K, Boltzmann constant, 1.38 times 10 to the power of negative 23, and the temperature in Kelvin. Okay, just now 20 plus 273 is 293 Kelvin. So the answer for the kinetic energy is 6.07 times 10 to the power of negative 21 joule. Okay, B question. Okay, answered. Kinetic energy, mean kinetic energy or average kinetic energy is 6.07 times 10 to the power of negative 21 joule. And lastly, question C, what is the RMS speed of the helium atoms? So for the RMS speed, we can use half m mean square speed. Okay, so for the C question, so we use kinetic energy equals to half m mean square speed. Because kinetic energy calculated already in B, so we can substitute the B value into the equation here. Okay, but before that we have problem, we don't know m, so we need to calculate mass of the gas helium. So this time mass of the gas helium is not given. So to calculate the mass of the helium gas, so we use this relationship in the previous lesson, or in form 4, form 5 also you've learned this. Okay, mass of the one atom, this is mass for one molecule, okay, for one molecule of the gas. So m per molar mass, okay, molar mass can get from the periodic table of the helium, okay, can get from the periodic table. So n is a number of molecules or atoms of the helium gas divided by Avogadro number. Okay, and also calculated in question A. Okay, so now we substitute all the values to get m. So cross multiply, we get nm per Avogadro number. Okay, so molar mass refer, okay, this one is for one molecule. This is mass for one molecule. So n is 1. Okay, n is 1. So remember, I repeat again, for the question, formula given here, m is mass for one molecule. Okay, so n is 1. So molar mass for helium refer to the periodic table, so it's 4 gram per mole. So you convert to kilogram, so becomes 4 times 10 to the power of negative 3 kilogram. And then the Avogadro number for 1 mole, the number of molecules is 6.02 times 10 to the power of 23. Okay? So we can cancel out the mole, we can get the mass in kilogram. So we get the answer, mass for one molecule is 6.64 times 10 to the power of negative 27 kilogram. So we substitute this value into the equation here. So mean square speed is equals to 2 ke per m. Okay, we cross multiply here 2 ke and then divided by m. So we substitute the 6.64 times 10 to the power of negative 27 into the equation here. And also we substitute the kinetic energy we have calculated in question B, 6.07 times 10 to the power of negative 21, okay, into the equation here also. So we, to get the RMS speed, so remember that RMS speed is square root of mean square speed. So we square root this value, okay. So we get the answer 1.35 kilometer per second. So you can answer in the prefix form, 1.35 kilometer per second. Okay, that's all for my video. Thank you for watching. So please subscribe to my YouTube channel if you don't want to miss any of my video.